Thanks for the introduction, very nice introduction. And thanks to the speakers for inviting me to give a talk here. It has been a wonderful week with very nice talks. So today I'll be speaking about eigenvalues of in-homogeneous Erdős random graphs. Before I begin, I must mention that this is a work with Arijit Chakraborty, who is a colleague in ISI Kolkata. Shukrit Chakraborty is a PhD student of both me and Arijit. And Frank den Hollander is in University of Leiden, and Matteo is a PhD student in Leiden. So first I'll start with inhomogeneous Erdős random graphs or inhomogeneous random graphs. Thankfully, Remco has given already a wonderful introduction to this area, and he has introduced a lot of the examples I'll be talking about, and so it has made my job a bit easier. First, I'll talk about what I'm interested in, the spectrum, then empirical spectral distribution, ESD, and one of the major parts would be an ongoing work with Arijit and Shukrit on the maximum eigenvalue, and some interesting ideas about how we proceed with the proof. So let us begin with the first thing. So our setup would be, so this is kind of the primary setup. We'll look at our vertex set is fixed, so it's like 1 to n vertices are there. And between each of the pairs, I put an edge independently with probability Pijn. So it's not, as you can see, the inhomogeneity comes from the fact that it depends both on I and j, and also n is there, it's already involved. And we allow, like, it's always for simplicity, like no self-loops, no multiple edges, and it's an undirected graph. One can do these things in directed graph, and it indeed becomes extremely interesting in that, and we'll not talk about those things. What will be interested out of the graph is the adjacency matrix. So adjacency matrix, as you can see, it's a just 1-0 matrix. So if you look at the ijth entry of the matrix, it's either 1 if there is an edge between I and j, or it's 0. And since it's an undirected graph, it's a symmetric matrix. And what are the entries? So entries are like Bernoulli random variables. It's 1 with probability Pijn, and 0 with 1 minus probability Pijn. So the graph looks quite deceivingly simple, but what we will be interested in is looking into the eigenvalues of this matrix. So let us see some examples. We have already seen many of these examples of generalized random graphs. One of the classic ones is where you don't have a dependence between I and j. Every connection is just epsilon n between some 0 and 1. And this was also introduced that if you are given some non-negative weights, and if ln is the sum of the weights, then Pij1 minus exponential minus wi wj by ln. So this is, and Pij almost looks similar, you just truncate it by 1 to make it less than 1. And this is the generalized random graph like wi wj by ln plus wi wj. And it was, as Remco pointed out, all these are asymptotically equivalent in some sense. What I want to point out here is, in these examples, so there is some kind of, especially this Chung-Lu, there is a product structure. If you look at Pij, it's like wi by square root of ln into wj by square root of ln. And this I'm pointing out already because this will be an important factor when we come later. This product structure in the connection probabilities will play a crucial role. So what we do is we take a general approach. I'm not entirely sure whether it's a general approach, but it's another approach. So what you do is you start with a function from the unit square to the positive half line. F is just a function. We are not imposing anything except symmetry. Fxy is equal to fyx. And there is a huge literature on why it is called graphons and all these things. But it's just a symmetric function from unit square to the positive half line. And then you set Pijn to be epsilon n into f of I by n, j by n. So what you are given is a general function, and from that you create an inhomogeneous Erdős random graph. One of the, so it's Bernoulli, it's Bernoulli with these success probabilities.
See this as kind of one special case for random matrices.
Okay, so in random matrices, so when you take, so for example, the classical random matrix, what you do is you take just IID normal 0, 1, or it has a fixed variance and fixed kind of mean or whatever is it. If it changes with n, things can change drastically, and we'll see that, how things change. One thing is closer to the random matrix is, what we are doing is, here we are considering why I'm naming this as still the Erdős, because we have independence among edges. When we toss, the coin tosses are quite independent. So there is independence among edges, which is missing in, for example, if you take a configuration model. So configuration model won't, you cannot direct apply these results to a configuration model, or even a preferential attachment model, to say that. Yes? I'll come to the assumptions. Initially, to describe the model, I don't need anything except it being symmetric, because I'm considering undirected graphs. So we take n large enough so that, so f is, so what we'll do is we'll assume f to be continuous. So f turns out to be bounded, and we'll take n large enough so that this is, otherwise to make this precise, I have to make it less than 1. Yeah, definitely, that is there. But we'll make that continuity assumption very soon. So, and this was kind of introduced already by Bolobash, Janssen, and Riordan in 2007. And if you see the upcoming book by Remco, in the first chapter, he deals a quite bit of things about phase transitions, and all these things about local weak convergence is already studied for these kind of models. A special case would be when your fxy is kind of product of two, it has a product structure like Rx into Ry. So in this case, Pijn is epsilon n R of I by n into R of j by n. So this is similarity with the Chung-Lu graph, where I told you there is a product structure. And this is generally the rank 1 case. So so rank 1, I'll come to it, why it is rank 1, because when you see the corresponding L2 operator arising out of it, it has just one eigenvalue. So that's why it's called rank 1 generally. And this is also an interesting graph, which was introduced by Lovas and Zaidi, and these people also studied. So what you do is you pick up uniform 0, 1 random variables in an IID fashion. And what you do is once you pick them up, you fix them. And then fixing that random variables, you can now define a graph where Pijn is just epsilon n f of ui into uj, ui comma uj. And these graphs kind of appear quite naturally in these graphon dynamics, and it's a quite famous example where these things apply. So these are some examples. So what we'll be interested in? We'd be interested in, so this is the random matrix questions we'd be interested in. So if you suppose Wn is any random matrix, and let lambda 1 to lambda n be its n eigenvalues, what you do is you put mass 1 by n on each of these eigenvalues, and look at this random measure. Why is it random? Because what will happen is, our matrices will be random, so lambda i's will be random, and this ln itself, when you put mass 1 by n on each of these lambda i's, it already produces a probability measure. So we want to look at the convergence of these probability measures, either weakly almost surely or weakly in probability. So many of the results we'll be stating can be pushed to almost sure, but we'll be sticking to an easier approach by proving convergence weakly in probability. Another question would be to look at the maximum eigenvalue. And that would be like coming to the part 2 of my lecture, where I'll be dealing with the maximum eigenvalue. And that's a more interesting question because more graph structures come into the feature. The convergence of ESD. So let me state the first main result here. So you consider an inhomogeneous random graph with connection probabilities as epsilon n, f of I by n, j by n, and you assume epsilon n going to 0, and n epsilon n going to infinity. And you assume f to be continuous. So what is happening here is you are in that regime where your average degree is unbounded. So whatever you call it, you might not call it a sparse case, it might be in the dense case, in the sense that the average degrees goes to infinity. So, so this is the setting, f is bounded, so you can take n large enough to make this less than 1. And then you look at the adjacency matrix, an, and you'll ask the question, where does the empirical spectral distribution converge to? So what you can show is there is a compactly supported symmetric probability measure. So it's symmetric about the origin, mu on R, such that this ESD, if you scale by root n epsilon n, which is going to infinity by our assumption, it converges to mu. Just, okay, so what is mu? I'll come to it, what is mu? Mu is very much dependent on what your f is. It's not very explicit. You can do that, but it's not like, it won't enhance you or give you any other information about it. The information won't be like enhanced by proving an almost sure result out of the probability. Only thing, one comment, that you can get rid of this epsilon n going to 0, but then you have to consider an minus expectation an. So you have to recenter them, and then you can look into it.
Removing the bias.
Yeah. So I'll come to what is known about mu. Now, if you assume that this fxy, this function is bounded away from 0, what you can show is mu is absolutely continuous with respect to the Lebesgue measure. This is one information one can get. What else? So, as in random matrix theory, it's very common to deal with Stieltjes transform, which characterizes a measure. So if you take mu, if you define the Stieltjes transform of mu to be g mu z, which is defined by this relation, it's the integral over the real line z minus x mu dx, where z is not, so you need to be properly defined, so z is outside the real line. So it's in the complex plane outside the real line. Then what you can do is you can write down a nice recursion equation, analytic equation out of it. So g mu z looks like it's an integral of a function hzx dx. So I'm introducing another function, hzx dx. What does this function do? This function is a solution of this kind of integral equation. It's a solution of this integral equation. It's an unique analytical solution on the plane. So as you can see, the first coordinate we restrict it to C plus, and the second coordinate is on 0, 1. So it's a unique analytic solution in that case.
Is to satisfy, you don't need that bounded away assumption?
No, I don't need the bounded away assumption. This is just plain, it comes from a combinatorial identity actually. So it comes from a combinatorial identity, and if you tell me like, can you give me an explicit expression? Yeah, sorry, I didn't see your hand. No, absolutely continuous means there is a density. No, explicit, see, nothing is explicit. Unless you give me an f, I can then try to find out what it is. Explicit, I don't know what explicit means. For example, I can write you a very complicated expression for hzx. I don't know whether that's explicit or not. It might have a very abstract expression, like in my terms. So, if you increase regularity, some things might get, so you can show perhaps the density is bounded and other things. So that one can do. That's definitely one can do. Now, so this is not, again, this is not giving any information unless like it's just a nice looking mathematical equation. So let us see some simple examples. When f is 1, so Pij is just epsilon n. It's the classical Erdős training. So how does this equation look like? So what happens in this equation, the f vanishes. You see there is no f now. What you do is you integrate both sides 0 to 1 dx. So what do you get is this integral 0 to 1 hzx dx. So I'm integrating this equation now. Now you look, this is g mu z. And what side is this? So if you separate out the equations, it's g mu z square. So what you get is a quadratic equation like this, g mu z square minus z g mu z plus 1. And you know, this is, those who, like if you are dealing with random matrix theory, it's very well known that this equation comes if you are taking mu to be semicircular. It's the unique solution is the, like, of this quadratic, like you can show that what you get is mu x is 4 minus, it's the classical semicircular law. So this equation kind of matches with what we know, and this result is not new. It was first shown by Ding Jiang, then Tran, Wu, and Wang like did it again in a improved fashion, and it also follows from this later works of Erdős, Knowles, Yin, and Yao. Another special case. So when fxy is the product, then you have a bit more complicated thing. So here hz u is a uniform random variable on 0, 1, and you have this, again it becomes a square like this. So it's a bit more complicated expression. But what comes to our rescue is free probability. You know, you can identify the Stieltjes transform through this measure, which is mu is like a mu semicircular law. This is a convolution, multiplicative convolution with a measure mu r. What is mu r? Mu r is the law of r of a uniform random variable. I'm not going to precisely describe what this convolution is, but you should think of this as a notion of independence when you are looking at non-commutative spaces like space of matrices. So it's a notion, it's a convolution arising out of, so when you are taking, say, product of x and y, where x and y are classically independent, you can get one convolution. And here you are also like, it comes to free independence, something called free independence. There you have, you can get this convolution. The main thing, this is well known. So one can identify exactly what the measure is in this case. Any questions till now? Okay, another, there are many examples. I'll just point out one of the examples. Yeah, that's really difficult.
No other cases, let's say Rx.
No, that's very difficult. That's kind of a bit difficult. Okay, so another case would be if you take, it's the Chung-Lu graph. So if you take din to be sequence of positive numbers, the maximum and the sum you denote by mn and ln, and you look at the connection probabilities which are of the product form, and you assume the conditions we had. So if you let mn square by ln be your epsilon n goes to 0 and n epsilon n goes to infinity, and you assume if you take this empirical distribution function out of these d1, d2, dn, it converges to a measure mu r, then you can show that the adjacency matrix, if you scale after root n epsilon n, it converges to that measure I described just now. So the spectrum of a Chung-Lu graph looks exactly, in the bulk, looks like this, with these assumptions. So what are the proof steps? Let me just very quickly say a few things. So first you do is, using epsilon n going to 0, what you show is the empirical distribution function of the adjacency matrix is very close to the adjacency matrix minus the expected. So expected an means I'm taking a matrix where each of these entries are expected value of the an ij's. So it's just expectation, entry-wise expectation of each of the random variables. Then what you show is, this is the crucial step, that the centered matrix, if you rescale, it looks like, you show it is close to an an bar, and an bar is a Gaussian random matrix with a variance profile. So each of the entries are Gaussians, so these are IID Gaussians, and you multiply it with them, f of I by n, j by n, and you scale it by everything by square root of n. So so from the Bernoulli random variables, you have to go to the Gaussian random variables. And this can be done, so there are many methods to do it. So we did it by an invariance principle of Chatterjee, which is kind of coming from Lindenberg's idea. So we thought it's an easier one to do, and this can be done. And there is so this, that's true in the bulk. The maximum eigenvalue, it will be very crucial that this comes up. And the crucial thing is now this is, so if F is 1, for example, this is classically known as the Wigner matrix. So with the Gaussian entries. So it converges to the semicircular law. This is very well known. So that's kind of one of the extension. And in fact, Gaussian random matrix with variance profile is also studied in these papers. So there are lots of papers about it. So let me come to the second part of the talk, which is, yeah, please. Yeah, the stochastic block model comes into the picture. What we can do, that's a very interesting question. Like, so we assume that F is continuous. What you can assume that F is just Riemann integrable. And then do the whole computation. So only thing what we need is F is Riemann integrable, and then you, this computation. And what you look at is, in the stochastic block model, you just look at functions which are constant on certain blocks of 0, 1. And then you look at the function, which is like indicator of sum of things, sum of measurable blocks. And then you do the computation, and then the expression is only the recursion you get. You don't get an added information out of that. But thanks for pointing that out, because like it comes into this, in this purview. So maximum eigenvalue. So now what we do is, we look into now, from now on, we'll look into only the rank 1 case, because that's already becomes a bit difficult to handle. So, so fxy is rx ry, and what we assume is f is Lipschitz continuous. One can relax this condition, and what you assume is the integral of 0 to 1 rx squared dx is 1. Let me first state the result. So what the result says, so remember, our LSD result needed the condition that epsilon n going to 0 and n epsilon n going to infinity. Now what you need is just not that n epsilon n goes to infinity, it should go to infinity faster than log n power 15. Yeah, the conjecture would be it should be just log n. But our methodology is just extend till log n power 15. We believe that it can be reduced to 6, but not, the methodology cannot be done till log n by n. And that's the optimal, I would guess, because
What is known in R equal to 1 case?
R is equal to 1, it can be reduced to, I think now, 4. 4. So there has been recent work, I haven't read of it, of Tikimirov, where he looks at different kind of phase transition on triangle counts and all these things, where he brings out this feature on how to get to log n by n by doing some tricks. So I haven't read it, but it's a very recent paper where he gets to that. Now, so what the result is that if you look at maximum eigenvalue and subtract the mean of the maximum eigenvalue, and if you scale it by epsilon power minus half, then it converges to normal 0 to integral of 0 to 1 rx cube dx. This is quite similar to what Kavita was saying, like if you take r to be 1, you get normal 0 2 with the exact scaling. Only thing is I'm not writing down what the expectation here is, because we cannot write down. I'll come to what the expectation behaves like, and then you'll see what happens. So this is the result. So any clarification about the result? No, that's a very good question, but in our computation, especially because we are using a moment method in many places, R is bounded is crucially needed. Because I'll come to what happens to the matrix when you center it. I'll tell you what happens when, what happens to the thing. Any questions? Yeah. No, it's not. It's a very good question. I'll come to that. It's not. Anyway, yeah.
Why are you using the Lipschitz property?
Lipschitz property, one can get rid of it. I'll tell you. It comes in a very minor place, and if you rescale this, instead of looking at maximum of an, if you rescale by some kind of norm of r of I by n, you can get rid of the Lipschitz and you can get a much more general result with just r continuous. So yeah, so how does the mu max in the first order look like? The maximum eigenvalue, which I denoted by mu max now, I am just dropping the an's. So the first order is n epsilon n. Note that I'm not scaling anything. This is just AN, just the random matrix, adjacency matrix AN, without any scaling or anything. So the leading order is n epsilon n. Then you have a leading order which is of this constant. And then you have smaller orders. As you can see, now from here, one thing is immediately clear. If you divide by n epsilon n, which goes to infinity, by the way, this vanishes, and the rest also vanishes. You can just, okay, it's an ugly expression, but you can show that this vanishes. So in probability, the largest eigenvalue of the adjacency matrix is like n epsilon n. And expectation is almost similar. If you see, the first order is same, the second one is same. So if you subtract this, mu max minus expectation mu max, whatever is happening is in these capital O's or the small O's. So it's not in the first two orders, so everything gets cancelled. So like the mystery comes after that. So how you deal with these things after that. So this is the first order result. So what you do is, another result is, how does the eigenvectors behave? So let Vmax or V, I'll denote it by V later, just to remove the notational complications, be the eigenvector corresponding to the maximum eigenvalue. Then if you take this vector Rn, which is R of 1 by n, 2 by n, R1, and just scale it by root n, then you can show that these two vectors are almost parallel. So it goes to 1 with very high probability. And when I say with very high probability, it means even that the probability of that not happening goes to 0 exponentially fast. All my high probability statements are like that, that if the statement doesn't hold, that event, the probability of that event goes to 0 exponentially fast. So it kind of, if R is 1, yesterday Kavita was stating this main result that if R is 1, this is kind of orthogonal, like this is the parallel thing, that it goes to 1. So I just want to mention, I forgot, I should have mentioned that the R is equal to 1 case was dealt by these people, and the proof is really complicated. Like, it took us really time to understand what is going inside the proof. So what is happening? So let me try to briefly, in the last 15 minutes, give you an idea on what is this mysterious happening. How does the Gaussian come in? Now, if you look at An, what you do is, you write it An minus expectation An plus expectation An. And this is my Wn. I'm writing it Wn just to indicate that it's like Wigner. And this was, Remco, what you were pointing out, that in the bulk, it doesn't see what is expectation of An. Everything comes from Wn, the centered matrix. That was what I was doing before, that everything comes from the centered matrix Wn, but not in the case of maximum eigenvalue. So what you see is, you see An can be written as Wn, which is a centered, so every entry is now centered, plus the expectation can be written in terms of that Rn vector. Rn was, just to recall, Rn was 1 by root n, R of 1 by n, R of 2 by n, like this, R1, this vector. So if you just write down this, then it's this. And what we know from the first part of my talk, that this thing, okay, I have written it in a simplified fashion, that when f is 1, say, this is in the semicircular regime. So this was the semicircular I derived. Otherwise, it's mu. Otherwise, it will be mu for the general, or mu. So what we know is, so Wn by square root of n epsilon n converges in this product case as mu r box times mu semicircular law. And what is this? This is a compactly supported measure. The eigenvalue. So this is, thanks, this is the ESD of this quantity measure. So this is what we know. So what we know is this quantity converges to a measure which has a support is bounded. And and it scales like root n epsilon n. And what we saw is, so what we have is now, so it's a rank 1 perturbation of a Wigner plus a rank 1, so it's a rank 1 perturbation of a Wigner matrix, Wn, theta n, Rn transpose, where theta n is your n epsilon n. Now it grows to infinity. In the open problem session, I was asking about what happens when theta n is independent of n, and that's a more interesting kind of problem, because what is happening is, if you look at the semicircular law, your density is bounded between -2 and 2. And what is happening is, so if you don't scale it, so it is like between this, Wn. And if you look at this matrix now, the expectation An, it has only one eigenvalue. And that one eigenvalue grows like n epsilon n. So which is much more. So it is somewhere here that it is n epsilon n. Here. So it is going beyond that spectrum. And it is growing. So that is helping. When it is not growing, then it's a trickier question, whether it's within the spectrum or outside the spectrum. It becomes a bit more subtle in that case. So how to solve these things? So I want to do this computation. So it's an easy computation. It's a very easy linear algebra, but I want to do this computation. So you write An as Wn plus theta n times Rn transpose, and let V be the eigenvector corresponding to mu x. What you do is, you multiply both sides by V. You multiply this equation by An V, Wn V, and Rn transpose V. Rn transpose V is a scalar, so I put it in the bracket here. And so you get this equation. Now, mu V is an eigenvector, so this An V is mu max V. This is, you know. Then what you do is, you just bring the Wn on the other side. What you have is mu x I minus Wn V. Then what I do is, I multiply both sides by mu max I minus Wn inverse, this quantity. Now you might ask, why can I do that? Why can I do that? Because I have to prove first the maximum eigenvalue of Wn is like beyond, is here. And mu max is lying somewhere there. So this quantity I have written is invertible with very high probability. So this is a very high probability statement actually I'm writing. So what you get is V, the eigenvector V is theta and Rn transpose V whole inverse Rn. So this is kind of an equation. And then what you do is you multiply again this side by Rn transpose. Here you put an Rn transpose and then you cut it, the Rn transpose. You just cancel it. Why can you do that? Why can you do this quantity? Because I have just shown you that you can show that Rn transpose V goes to 1 with very high probability. So it's a non-zero quantity with very high probability. So you can do this cancellation. And what you get is an equation or like this. 1 is equal to theta and Rn transpose inverse Rn. So let us look into this equation. Just take out the mu max out of this inverse. Then you get an equation like this. Mu max is equal to theta and Rn transpose I minus Wn mu max whole inverse Rn. Now what we do, it's like 1 minus x inverse. If mod x is less than 1, then you expand the inverse. And why can we do that? So suppose we can do that. Suppose you can just expand this 1 minus Wn by mu max whole inverse. Then you have an infinite series.
So here you can do that with high probability.
These are all statements with high probability. I'm not writing, these are in fact statements with probability of not happening going exponentially to 0. So these are very high probability statements. So as you can see, this is, if you look at this equation, this is like a stochastic power series or Laurent series where you have mu max as a fixed point. So it's like z is equal to theta n times something, some stochastic coefficients divided by z power n. So it's a fixed point of an stochastic equation here. So, and theta n is n epsilon. Now why is this inverse series valid? What you can show is, what I was claiming is if you look at the spectral norm of Wn, it is like twice this R infinity is coming into picture, then root n epsilon n, and then you have some errors. Now, you are asking what happens if R is unbounded? You can see that this is going to infinity. So kind of our methodology needs you need to take care at what rate or how it is behaving when you're cutting at some point, like how your function you're taking, how the tail of that function is. So it's a very good question, but it doesn't fall in this regime. So R is unbounded is a very interesting case which would arise out of here. Because it would make the Wn to be unbounded, and then it can compete with this one isolated eigenvalue which is lying on the other side. Yeah, that's a very good conjecture. That's a very good. You made me realize now that's a very good conjecture that.
We see this occurring in many more cities.
Yeah, and it would relate to some like other cases where you have like similarities with where you have third moment or think finite, and that would kind of.
So the third moment.
That's a brilliant comment. That's a brilliant comment. Any questions? Okay, why is this again finite? As I was saying, Wn is growing like root n epsilon n. Mu max is going like n epsilon n. So if you look at norm Wn by mu max, you can show that this is strictly less than 1 minus some positive constant c. And you can do the inverse now. So this is again with very high probability. You can do the inverse on a very high probability event. Okay, so let us look at this ominous series we have. So we have this series. So let us look at first few terms. The first term, k is equal to 0. This is just like Rn transpose, which is norm Rn square. Then n epsilon n, which is outside. The first term, k is equal to 1, is just Rn transpose Wn Rn. And then you have this factor. And rest of the terms are there, which is in the green. Interestingly, this term, mu max, I have already shown, is of the order of n epsilon n. So this term goes to 1, the red bracket. The red bracket goes to 1 in probability. The remaining term, if you scale it by epsilon n power minus half, Lindeberg CLT would show you that it converges to this quantity, which we actually need to appear. And what about the rest of the terms? So let us look at the k is equal to 2 term. The k is equal to 2 term, n epsilon n by mu max square, Rn transpose Wn square Rn. What is happening is, this goes to 0 only if your epsilon n, root n into epsilon n goes to 1. Goes to infinity, sorry. Root n into epsilon n goes to infinity. But if you recall, our basic condition was epsilon n is greater than log n power something by n. So if you just give me the assumption that you have an epsilon n, which is like root n epsilon n going to infinity, you can just center by that quantity, mu max minus n epsilon n norm Rn square, and scale it by epsilon n power half, you will have the CLT. But if you want to reduce it, then you are in trouble. Because if you just assume this quantity, epsilon n is something like a plus epsilon, it fails, it goes to infinity. And then, okay, there is a bit of work, I'm just talking about the third term in this. There is a fourth term which is going to 0. It needs more work because it's a series. A series where each of these terms goes to 0. If you sum that infinite series, it need not happen that that would go to 0. So you need going to 0 very fast. Okay. So what happens is, the main key lemma we are proving is that mu max looks like a constant x naught n, which is a very important constant, times plus Rn transpose Wn Rn, which is the one which is giving our CLT, plus an error psi n. What is psi n? Psi n is capital OP of, so we are finding a bound for this, which is a very good bound which works for our regime. And what is this x naught n? X naught n is, we looked at the series, now you don't take the infinite series. You truncate the series at some point, at say log n. And you, instead of that random coefficients, Rn transpose Wn power Rn, you take the expectation. This is a deterministic equation. Whatever solution you have, would be a deterministic solution. Firstly, you have to show that there is a solution. There will be a unique non-negative solution for this equation. In fact, the solution would lie more than n epsilon n. So there is a solution like that. And that needs a proof because, and this is, to show that this is non-negative already requires quite a bit of work. These expectations are non-negative because there is lots of going on in there. So this deterministic solution, x naught n, can be written as this, and OP of this. What else can you do is you can show the expectation of this also has the same bound. Now look, if I have this equation with very high probability, suppose I can take an expectation of this equation. What happens? The expectation of mu max is again x naught n, and what is the expectation of this quantity? This is sum over some centered elements. Sum over some weighted, sum over some centered elements. So it's mean 0. So the expectation of this quantity vanishes. And then you have an expectation of this, which you know is again bounded by that quantity. So mu max minus expectation, what you are left out with is this quantity, which is your central limit theorem. So what you are left out with is just that part. And then you show that the error is of the correct order, and you can show that. As you can see here, you need log n, growing like log n power 14 by n. You need that bound here. Okay, some future directions. I have just 1 minute to wrap up. Some future directions would be to how to extend this to an infinite rank or a finite rank case. So this is a quite, for example, we looked at this graph which 1 minus exponential minus wi wj by ln. It is not of a product form. But if you expand this, then it's like some of these things. Like you can write it as sum of certain product matrices or product form. So
in your case, second one is Tracey-Ullman regime.
it's known. It's a very recent work where it's known that in the homogeneous case, only in the homogeneous case, it's known that it's Tracey-Ullman. In the non-inhomogeneous case, it might not be Tracey-Ullman. That's what I am writing. It's in the Tracey-Ullman regime. It would be a deformation, a bit of deformation of the Tracey-Ullman. It won't be a direct. So what is happening? You have to assume the first eigenvalue would be more than the others. It's just for simplicity. Then what you can show is in probability lambda 1. And what is interestingly will happen is first k of the eigenvalues will fall as a Gaussian. Then it goes into, so what will happen here was one eigenvalue was outside the spectrum. Now there will be k eigenvalues which will be outside the spectrum. And they will all fall in the Gaussian regime. So it will be sort of a multivariate Gaussian. And the rest one would be again in the classical Tracey-Ullman kind of thing. So this is a difficult to prove. I don't think we can immediately manage this Tracey-Ullman regime, but at least we are trying for the Gaussian part, which is already becoming difficult.
How do you know that the first k eigenvalues are outside?
Yeah, they would grow at the rate of n epsilon n actually. That you can prove.
So you're assuming something about the lambda j then?
The lambda j's are just this eigen expansion. So lambda 1 would be more than this thing. So yeah, they would be just, if you look at this rank 1 perturbation I had, if you go and make it a finite perturbation, there would be this n epsilon n which will be lurking behind all these expectation matrices. The rest part would be in the Wigner matrix, and there would be k eigenvalues. Yeah, order of the magnitude. But what you can show is that this quantity will be still, like if you assume lambda 1, then this will be lambda 1. And if you center at least the maximum, we have a proof, we are writing down some specific estimates, but at least the maximum eigenvalue will be in the Gaussian regime. We can guarantee that. Another is, which is a difficult quantity, I don't have time, but interesting is in a recent work by Dembo and Lubetsky, where you are again in this regime where your degrees go to, average degree goes to infinity, they showed the empirical distribution function for the configuration model. If you make an appropriate scale, it goes to a measure which I was pointing out here, just like the product rank 1 case. So as you can see, we have seen it many times, even in Remco's talk, that the configuration model can be, so once you know something about the configuration model, you can go back and tell something about the generalized random graph. So this is kind of coming here again. So, and the proof also, if one goes through the proof, one sees that yes, indeed, an inhomogeneous Erdős random graph comes in there. But I don't know, again, dealing with the maximum eigenvalue would be a very good challenge to extend this, because it's a much more complicated problem. And thank you for your attention. Any questions? Yeah.